why thermodynamics is important. Consider an LNG carrier. The purpose of an LNG carrier is to contain and carry LNG. So we have to design the cargo tanks. Another purpose of LNG carrier is to load and unload the cargo LNG. So we have to design the cargo handling system. So only after the cargo tanks and the cargo handling systems are designed, we can design the hull, the structure, the safety systems, and so forth. Thermodynamics explains the behavior of the material. In this case, I mean cargo LNG. And the conservation of mass, momentum, and energy can give us the heat and mass balance around an equipment. And based on the heat and mass balance, we can design the equipment. In this case, the cargo handling system. Offshore plants are usually handling oil and gas. As you know, 80% of our daily consumption of energy comes from oil and gas and coals. We call them fossil fuels. Offshore plants include production platforms, FPSO, FSRU, and LNG FPSO. In short, FLNG. These offshore plants are more equipment intensive than ships. The ships are a very simple thing compared with offshore plant. So offshore plants are more engineering intensive, more safety critical, more difficult to fabricate. So that's why offshore plants are more expensive than ships. For example, an FPSO is usually, in an average sense, 10 times expensive than the most expensive carrier, LNG carrier. I mean that for rough estimate, LNG carrier is about $0.2 billion, but one FPSO is simply $2 billion. We expect that LNG FPSO or FLNG would be $4 billion or more. So in short, thermodynamics gives us the information for process design, and based on the process design, usually we carry out kind of process simulation. We can get the process information, and we can design equipment. Then follows the others like structure, hull, and so forth. Unfortunately, it's very hard to deal with directly the offshore plant. So in this course, I will take an LNG carrier as an example. Any questions? Feel free to interrupt me when you have any questions. Some lines are missing. I don't know why, but actual line is like this. It's a schematic diagram for cargo tanks and the cargo handling system for LNG carrier, a very simplified version. In this carrier, we have 4 cargo tanks, and the internal pressure is near atmospheric, close to 1 bar. Actually, it is in the range of 1 0.05 to 1.25 bar. And the storage temperature is around minus 160 degrees Celsius. And I don't know why, but this is the actual line. In your manual, I think you can find the lines in the correct position. When we are to load and offload the LNG, we use this line. We call the big piping LNG header. And through this line, LNG is loaded and offloaded. When we are needed to offload the LNG, we use the submerged pumps. Actually, there are 2 pumps per each tank. Because of the big temperature difference between the stored cargo and the surroundings, there are big heat ingress. So this heat ingress heats up the LNG. So part of the LNG, as you expect, will vaporize. In short, boil off. So we call the gas, gas is not the correct term, vapor. Vapor, we call the vapor boiled up gas. In short, BOG. The BOG should be removed from the cargo tank and re-liquefied in a dedicated system. The system is called re-liquefaction system. This is the composition of LNG and the BOG. The majority of the LNG is composed of methane and ethane. Are you familiar with methane or ethane, that kind of naming? If you smoke, you are familiar with LPG lighter. That material is around propane or butane. Okay, so methane, the majority of the LNG is methane and ethane. Methane takes nearly 90%. Consider the BOC concentration. Nitrogen takes nearly 10%. Check the nitrogen concentration in LNG. It's just a trace, close to 0. But because of the thermodynamics, because of the thermodynamic property of nitrogen, BOG contains a lot of significant amount of nitrogen. Because nitrogen is lighter. Lighter means it has higher boiling point. You understand, guys, in Changwon University? I think so. This is a cargo tank type. There's something wrong with the slide. There are 2 types of cargo tanks for LNG. One is spherical type is called most spherical cargo containment system. Another type is box. It looks like box, as you see on your manual. The box cargo containment system is developed by GTT. These 2 companies are several years ago merged, and their company is called GTT, a French company. This is the picture of LNG carrier. Is both membrane, both spherical cargo containment system. This is the membrane cargo containment system. Because there is some significant amount of heat ingress, it is natural to install a heavy insulation layer. So on the spherical tank, we apply a thick layer of insulation. The material is usually polyurethane foam. But the membrane insulation system is a little complicated. There are several layers. And if you check your homework, you can see the materials for the layers. Pressure protection. Cargo tankers are designed to carry the cargo near the atmospheric pressure, but we have a BOG. BOG will try to increase the internal pressure. So we need to reduce the pressure. So such kind of action, such kind of design is called pressure protection. We are not going. What I mean that pressure protection doesn't mean to protect the pressure. It means protection against pressure. When you say fire protection, we don't mean we wanted to protect the fire. The meaning, the actual meaning, the correct meaning is you wanted to do something against fire. Okay, so pressure protection is some measures that can be operational or they can be design. Some design or operational protections against the pressure. When the pressure is too low, when the tank is vacuum, we vaporize part of the LNG and insert the vaporized LNG into tank. Then we can increase the pressure. It's very simple. When the pressure is high, we need to remove the VOC from the cargo tank. And in this example, we liquefy again the VOC and generate the LNG and return it to the cargo tanks. If the pressure is too high, there are two levels. Pressure is high and the pressure is too high. When the pressure is too high, we have to protect the tank against the pressure. So when the pressure is too high, it is kind of emergency. We need to protect the tank against the LNG leakage. So in this case, we open the safety valves. There are two safety valves on each cargo tank, and the VOC is vented. And usually the VOC, as you know, VOC contains some methane. That means it's a greenhouse gas and flammable, very dangerous. So it is usually incinerate. Incinerate means burned in the gas combustion unit. Sorry for the erratic screenshot. Let's skip this one. This process is developed. These detailed pictures of the reliquefaction system developed by a consortium of Korean companies, including the shipbuilding majors and the leading company was Shenyang Heavy Industries. So this is a patent process. Actually, I was deeply involved in the process design of this process. So what I mean is the process is somewhat complicated, more complicated than meets your eyes. What I actually mean is this slide, thermodynamic questions. There are a lot of challenges to the system design, like structural design, ship motion, mooring. So in this case, we concentrate on the thermodynamic questions. So thermodynamic view of the system design. And we concentrate on energy transfer, heat transfer, and system design. Let's divide the system into two subsystems. One is cargo containment system, and the other is a BOG liquefaction system. Cargo systems consist of cargo tanks and pumpers, installations, and headers. BOG liquefaction system has two cycles. One is a BOG cycle, and the other is a nitrogen cycle. These are the specific questions. First, what is the amount of the heat ingress? Second, what is the amount of BOG generated? And what is the composition of the BOG? And what is the transient behavior of the pressure increase within the tanks? These kind of questions are kind of thermodynamic questions concerning the system. For the BOG liquefaction system, we can come up with this kind of questions: minimum and actual energy required for liquefaction. I mean, how much energy do we need to liquefy 1 ton of BOG? That means if we answer the question, we can decide the capacity of electric generator. Okay? And the thermodynamic model of the machinery components, I mean, we have compressors, heat exchangers, and expanded turbines. So we needed to know the process condition to design this equipment. What I mean is, when I say equipment design, it's not about the mechanical design. I mean that what I mean is we needed to specify the conditions, boundary conditions for choosing a correct machinery. To answer these questions, we need some background. The first is the conservation of energy, mass, momentum. The conservation of energy is highly related with thermodynamics. I think you're already familiar with conservation of mass. We call it canoniere. And in your fluid dynamic course, you already have studied the conservation of momentum. We call it equation of motion. And another background is equilibrium and the vapor pressure dependence on temperature and the multi-component phase equilibrium. Okay, we need this kind of background to answer the 6 questions. For the last 4 days, we will follow this path. First, we will study laws of thermodynamics. First, second, and third law of thermodynamics. And these are kind of non-distributed and steady description of the system. And our reasoning will be based on ideal gas. What is non-distributed? What is the meaning of being non-distributed. What do you mean when we say the system is non-distributed? No idea? Non-distributed means there is no spatial dependence, and the system has no spatial and the position. And when I say the temperature of this room is non-distributed, that means the temperature is the same at every corners of this room. Okay? Conservation of energy, mass, and the momentum. First, we'll study microscopic description. Usually, I think you are familiar with the microscopic balances. I mean, the differential form of continuity and equation of motion. Okay? And in system design, the more important thing is macroscopic balances. And when we deal with the systems, we cannot describe all the conservations based on differential equations. In the differential equations with distributed variables, it's really impossible if we employ that kind of approach. So we will employ macroscopic balance. And the last path is phase equilibrium. First, we'll talk about pure component phase equilibrium. Then we'll move to multi-component system. Because of the limit of time, I will just touch the surface. So you have interest in this area. Recall your memories when you are the freshman and sophomore, and check the textbooks. I recommend it. Okay, any questions before we study the law of thermodynamics? Any questions from you guys? No question? No question? Okay, let's move to laws of thermodynamics. You already know, I'm sure, the laws of thermodynamics. There are 3 laws of thermodynamics. First is energy cannot be created or destroyed. You agree? If you can completely understand the meaning of this statement, you don't need to be here. And you can miss the next class. The second law of thermodynamics is the entropy of the universe does not change for reversible processes and increases for spontaneous process. Here we have 2 confusing terms, reversible and spontaneous. I will explain later if you don't know. And the third law of thermodynamics is at 0 Kelvin, the entropy of a pure, perfect, crystalline substance is 0. I'm sure you know the meaning of the first law of thermodynamics and the last law of thermodynamics. But the second is a little confusing. Let's define some basic terms. First, heat. The heat is the one of the terms we are using in our daily lives. It is the form of energy used to cause the temperature of an object to increase. It is simply heat up, warm up an object. So heat transfers from a hotter object to a cooler one. But this statement holds only for closed system. For some open systems, heat can flow from cold side to hot side. You may heard heat pump. Heat pump means we can pump up the heat from lower temperature to higher temperature if the system is open. We'll talk about open and closed system later. One to slide later. Work is the form of energy to cause an object to move against the force. Simply, work can move an object, okay? Like lifting an object against the gravity, or hitting a baseball against the stagnant or the stagnant air. And energy is the capacity to do work or transfer heat. Thermodynamics is coined by combining two terms, thermal plus dynamics. Thermal means heat or energy, and dynamics means action or motion. So thermodynamics is the study about energy and its transformation. Systems and surroundings. System is the portion of the universe singled out for study. So system is just the entity of our study target. So system is just the target space. And the surrounding is just the rest of the system. It's clear? And open and closed system. Open system means a system that can exchange both matter and energy with the surroundings. That means energy and matter can cross the boundary of the system. That kind of system is called open system. Closed system means a system that can exchange energy with their surroundings, but the matter cannot cross the boundary. So in this example, this is the open system, and this is the closed system. And the statement that heat flows from hotter one to colder one only hold for closed system. I mean, when there is kind of mass transfer across the boundary of the system, heat can flow from colder side to hotter side. If you have some interest in that kind of statement, check the heat pump. Heat pump. Intensive and extensive property. Extensive property depends on the size of the system, like mass, volume, energy. These are extensive properties. The intensive property is independent of size of the system, like density and the pressure, temperature. These are intensive properties. So the natural approach is to define an intensive property by through some manipulation. The typical manipulation is that an intensive property can be transformed into intensive property if we divide it by a proper extensive property, like density. Density is defined by combining two extensive property, mass and volume. And molar volume is defined by the volume divided by mole, and energy per mass. We usually use the term like specific enthalpy, specific entropy, specific blah blah. Those kind of energy means energy per mass. Okay. As you know, there are two kinds of energy. They call your middle school ages. There are two kinds of energy. One is kinetic, the other is potential. Kinetic energy is energy of motion, and the thermal energy is the type of kinetic energy a substance possesses because of its temperature. It applies to the gas. The temperature of a gas is kind of representative of the velocity of the gas molecule. And potential energy is given by some relative position of molecules or an object. And one example is gravity. As you know, the potential energy of an object, which has a height is rho, mass times gravitational acceleration and height. Okay, it's the most popular potential energy. There are another types of potential energy. One is electrostatic process and between charged particles. The other is the attractive and the repulsive process within substance. We call the energy chemical energy. A simple example is combustion, heat of combustion, okay, heat of melting, like that. That kind of energy is stored in the relative position of molecules or the electrons, okay? Unit of energy, in SI unit we use a joule. 1 joule is defined by this equation. You know the form of the kinetic energy, so you can check the mass and the velocity. And calorie is the amount of energy needed to heat up 1 gram of water by 1 Celsius, because the heat capacity of water depends on the temperature we use. We specify the temperature, from 14.5 to 15.5 Celsius. BTU is the British thermal unit. 1 BTU is close to 1 kilojoule. Okay, let's move to first law of thermodynamics based on their defined terms. First law of thermodynamics states energy cannot be created or destroyed, but conversion of energy is possible and transfer of energy is possible. it's very hard to use. Conversion of energy is possible and transfer of energy is possible. Conversion of energy means one form of energy can be converted to another form of energy. I mean, the potential energy can be converted to kinetic energy, as you well know. So potential energy loss in this case is exactly equal to the kinetic energy gain if there's no energy transfer to the surroundings. And transfer of energy means the energy can move from system to surroundings and vice versa. So energy lost by the system is exactly equal to the energy gained by the surroundings. So then where can we apply the law of thermodynamics? As we can apply it to the analysis of the changes in the internal energy. What is internal energy? Internal energy is kinetic energy plus potential energy of a material. So let's start from the classical ideal gas. Classical ideal gas, the internal energy of classical ideal gas. Classical means equipartition principle holds. And that means one molecule has average energy 1/2 times K times temperature per mole. Here K is the Boltzmann constant. So for mono atomic gas, I mean the gas has one molecule like helium, neon, argon. This kind of gas has three translational modes in X, Y, Z axis. The motion has three degree of freedom. So the kinetic energy is just 3 times the unit energy for one mode. For diatomic case, there are additional 2 rotational modes. So the kinetic energy increased by 2. So the total kinetic energy is 5 times 1/2 times K times temperature. So internal energy U is proportional to the number of molecules times Ke per molecule over pressure times volume. And in short, the system has n number of n molecules, and each molecule has this amount of kinetic energy. So the kinetic energy of the system is just n times this amount of energy, and it's just 3 divided by 2 times pressure times volume. It's kind of classical ideal gas approach. For example, what is the internal of the gas? We consider monoatomic gas helium. Volume is 0.05 cubic meters, and the pressure is 1.10 to 7 Pascal, and temperature is 300. Then we can, there are 2 approaches. In this case, we know pressure and volume, so we can calculate this. Or another approach is we can calculate the number of molecules within this system. And we know K and temperature. So we can calculate the internal energy of a molecule. So for an ideal gas, temperature is just kind of parameter for the kinetic energy. Internal energy itself, like the enthalpy, the absolute value of the internal energy or entropy is not important. The change, the difference of a process is important. Okay, so now we are concentrate on the change of the internal energy. So how to calculate the change in the internal energy? So internal energy is a function of temperature and the pressure and the volume. We can estimate the difference in internal energy from the difference of temperature, pressure, and the volume. Okay? So the first method, since U is a function of temperature, you can change T by adding or removing heat in order to change the internal energy. So the change in U is proportional to heat. Okay? That means internal energy change is proportional to a heat transfer. Another method to change the internal energy U is, since we use a function of P and pressure and volume, we can change pressure or volume by doing or receiving work. So in this case, internal energy change is proportional to work. Okay? So by convention, we define work to be positive if the system does the work on the surrounding. There are some reasoning. So I think you already know why it is convenient to take a positive sign when the work is done by the system. So just check the slide. The total work done is given by this equation. The first is just the work is given by force times displacement. It's the general law of dynamics. Okay? So if we consider the small amount of infinitesimal amount of work, dW is equal to F dy. And in this case, piston moving case, F is equal to pressure times area. So PdV, dW is PdV. We are getting back on track. So dW is equal to PdV. So the total work is given by integration of PdV. So to evaluate the integral, this integral, you must know P as a function of volume. That means we have to know how the pressure depends on functionally on the volume. So work depends on path, where P changes with volume. Okay? So we say work is path dependent. Right? another to estimate total work done. In other words, to estimate the integral of this equation, the physical meaning of PDV means we have to, this is just the area under the PV curve. Okay? This is the meaning of this integral on a graph of pressure versus volume. So the painted area is the integral of this PDV, and it is the total work done by the system, right? I think one slide is missing. So if we can construct the several paths where the pressure depends on volume in a different way. So in this case, the work is just this area you've just seen, and in this case, this area. In this case, this area. It's just the work on a graphical representation. Okay. So combining the change in internal energy. Internal energy change is proportional to minus work, and in internal energy proportional to heat. We get the first law of thermodynamics of a closed system. So internal energy change is Q minus W. Okay? Let's see some slide. Isoprocess is the process where one of the thermodynamic variables is kept constant. In isothermal process, temperature is kept constant. Isobaric process keeps temperature constant. Pressure kept constant. Isochoric or isometric process, volume is kept constant. There are other isoprocesses like isothermal, isentropy, isenthalpy, adiabatic. All these are kind of some thermodynamic variable is kept constant. So for the first three processes, isothermal, isobaric, and isometric, if you use the PV diagram, you can visualize the change of the internal energy as well as the work and the heat. Okay. Isochoric, isometric process for ideal gas, the volume of the gas is kept constant. So in PV diagram, the pressure is kept constant and the volume is changed. It's the same slide. I think the equation is missing, right? Yes. Sorry. So in this case, work is given by pressure times volume change, and there is no volume change. So work is 0, and the Q is just because Q is just delta U plus work. So because work is 0, Q is exactly equal to delta U. So delta U is equal to, is given by the temperature change. So we can derive this equation. Delta U is equal to 3 over 2 N. N is the number of moles, R delta T. So since Q is equal to delta U, you can express this kind of equation. And this is the definition of this term. I mean that Q is equal to 3 over 2 times R times number of moles times temperature change. So this term, 3 over 2 R, is the constant volume specific heat. Okay, so I think you may remember this relation for the from your elementary thermodynamic course. Can you remember this equation? So this is the reasoning why the specific volume constant volume specific heat is equal to 3 over 2 times gas constant. Another process is isobaric process. In this case, pressure is kept constant, but volume changes. So following the same reasoning, work is given by this equation, and if we apply the ideal gas law, PV is equal to nRT, you can extract delta U and delta Q. So the CP, constant pressure specific heat, is equal to 5 over 2 times R. So Cp is greater than Cv by R, the gas constant. When the temperature is kept constant, we can derive this equation. Work is nRT ln V2 over V1. If we apply the ideal gas law and integrate the PDV, and Q is just nRT blah blah blah. First law of thermodynamics, it's a summary of the first law of thermodynamics. Energy cannot be created or destroyed, but conversion of energy and transfer energy are possible. And the work depends on initial and final state, and the work depends on the path, how P varies with V. So work depends on the states and the path. So we say work is path dependent. But Q minus W, and if we combine work and heat transfer, Q minus W, in short, the internal energy does not depend on path. Work depends on path, Q depends on path, but Q minus work, Q minus W is not path dependent. So it depends on the just final and initial condition. So that's why we call it Q minus W is the change in internal energy. There can be other properties like Q, W, Q plus W, Q minus 2W. But these these combinations cannot give the property, the state dependent. Only Q minus W depends on the initial and the final state. So we call Q minus W the internal energy. Let's move the second law of thermodynamics. Second law of thermodynamics, the entropy of the universe does not change for reversible processes and increases for spontaneous process. What's the meaning of reversible and spontaneous? Spontaneous process. Consider two bulbs. One is evacuated. In this case, the bulb A is evacuated, the vacuum bulb, and bulb B is filled with air, and they are connected. When the valve is opened, the air molecules in the second bulb, bulb B, will move to bulb A. So this process is spontaneous, and that it occurs without any external help. But process from this to the original case is not reversible, and we need some energy. The system, the process needs some energy to move from here to there. Okay? So spontaneous processes are those that can proceed without any outside intervention. So I guess that's the meaning of spontaneous. Spontaneity depends on the surroundings. What I mean is, consider the two processes. Process A is freezing of freezing of water, and the process B is just the reverse of the process A. The melting of ice. Here we have water, and we have, on the other hand, we have ice. We consider this process and this process. So the process B is just the other way, the opposite process of process A. So when the surroundings is above 0 Celsius, process B is spontaneous. I mean that the ice will melt. Below 0 Celsius, process A is spontaneous. The water will freeze. So depending on the surrounding conditions, process A is spontaneous. Sometimes the process B is spontaneous. Let's define another process, reversible. Reversible process where the system changes in such a way that the system and the surroundings can be put back in their original state by exactly reversing the process. And we can, when we reverse the process, we can say reversal process. And in this case, consider the small temperature difference between system and surroundings. When the system temperature is a little higher than the surroundings, the heat will move from system to surroundings. When the system is a little colder by a very small amount, temperature difference, the heat will move from surroundings to the system, right? So when the temperature change is very small, in a technical term, infinitesimally small. it means very, 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 very small. We can say that these two processes are reversible. If we reverse this process, we can get the second process. Irreversible process means just irreversible process cannot be done by exactly reversing the change to the system. And the important thing is that all spontaneous processes are irreversible. All spontaneous processes are irreversible, and all real processes are irreversible. That does not mean all real processes are spontaneous. This statement just means all spontaneous processes are irreversible and all real processes are irreversible. Entropy S, there are many terms like entropy, enthalpy, Helmholtz free energy. That kind of energy cannot be measured directly, right? There is no equipment in the world to measure the entropy directly. They are kind of derivative energy. We can only measure mass, temperature, pressure, this kind of things. We cannot measure density directly. We measure mass and the volume and derive the density based on mass and volume. And entropy, enthalpy, Helmholtz free energy, that kind of energy are derived from the thermodynamic variables like pressure, temperature, volume. And entropy is that kind of derived the concept. Entropy is a term coined by Rudolf Clausius. You may have heard about him in the 19th century. He was convinced of the significance of the ratio of heat derived, delivered, and the temperature at which it is delivered. And simply, Q divided by T is very important. He had that impression, had insight, and it can be thought of as a measure of randomness of a system. So it is related to the various modes of motion in molecules. Anyway, like total energy, E, and enthalpy, entropy is a state function. State function means we can define the difference by knowing the initial and the final states. Path is not important. Okay? State function means state just determines the value of the function. Path is not important. For process occurring at constant temperature, the temperature is constant. In that case, entropy change is just Q divided by T. But one constraint is that Q should be reversible. So as I told you one or two slides ago, there is no reversible process in the world, and all real processes are irreversible. So there is no actual way to measure Q reversible. Okay, Q reversible only exists in our imagination. So we can define in this way. The second law of thermodynamics means the entropy of the universe does not change for reversible process. That means for reversible process, the entropy change of the universe is equal to 0. And the entropy change of universe has two terms. One is system, one for surroundings. They can be positive or negative. But the sum of entropy change of system plus entropy change of surroundings is equal to 0. In other words, the entropy of the universe is 0 if the process is reversible. But as I told you, there is no reversible process in real world. The second is irreversible process. The entropy should increase. It's the real one. We can say that the entropy. Then you can say that the entropy of the Earth is increasing. No, it can or it cannot be. Cannot. That the entropy of the universe is increased. Okay, the universe is kind of a closed and isolated system. There are many real processes. There are many irreversible processes within. But this does not necessarily mean that the entropy of any individual system is increasing. The Earth entropy can increase or decrease. For example, if there were not for the sun, the temperature of the Earth will fall and fall and fall. So in that case, we can guess that the entropy of the Earth is decreasing. So what I mean that the entropy of the system can increase or can decrease. Consider the entropy on a molecular scale. We have more molecules. That means there are more states. So the entropy is increased. If the temperature is higher, the energy state is higher. Excuse me. And we can expect more entropy, and the entropy is increased. When the molecular structure is less regular and less structured, compare the gas, liquid, and solid. Consider the molecular structure of the three phase. That the gas is less structured than liquid, and the liquid is less structured than solid. Concerning the regularity of the molecules, so we can say that gas has larger entropy than liquid, and the liquid has liquid has larger entropy than solid. Sometimes the regularity of liquid and solid is comparable. In that case, this kind of statement cannot hold. For example, as you know, the glass is liquid or solid. Yeah, in a common sense, glass is solid, but we can consider the molecular structure. Glass is just high viscosity liquid. You agree? The glass in the window is a liquid. That's why it don't have any crystalline structure. Amorphous. And this, I think this is the last slide. The third law of thermodynamics is at 0K, the entropy of the pure perfectly crystalline substance is 0. Considering the states or temperature structure of the molecule, 0K is the lowest temperature. Pure substance has only one kind of molecule. Crystalline means is the perfect structure. So at 0K, the entropy of perfect crystalline is 0. So as you know, we don't have this kind of structure, or we never can reach 0K. It's a kind of concept. Okay? Okay. That's all I prepared. Do you have any questions?